All right, good morning, everybody. Welcome back to Elements of Calculus 2. Today, we're going to be talking about improper integrals. Okay, and I think the best way to start this is just I start with an example here. So the idea of an improper integral, say we have the integral for 3 off to infinity of 1 over, and this is x plus 1 cubed. Okay, now the idea behind the improper integral is you see this infinity here? That's not actually a number. We always want to go from A to B. We might have function values in here, but they're functions that can be evaluated. We don't want infinities inside of our integrals. So the first thing we're going to do is we're going to change this to the limit as A approaches infinity. It's whatever letter you like, A, B. We prefer you didn't use C because that has a job. Okay, but we have other letters that we didn't use yet. Of the integral between 3 and A. And I'm going to go ahead and change this to a calculus problem. So we're going to say x plus 1 raised to the negative 3x. Everything else works exactly the same as you think it ought to. Okay, so we're just going to integrate this as normal. Now, one of the standards that we have is that students will be able to write appropriate mathematics. When you're dealing with improper integrals, you have to go ahead and put this limit on a regular basis. So all the problems we have for this limit is going to follow us around the entire problem. And I'm sorry for that. That is one of the standards we have. So that is one of the things you get graded on. Not my class. Almost every calculus class that teaches this topic will be exactly the same way. So everybody pretty much has to go through this writing the limit over and over and over. The calculus teacher will be much happier with you if you do this. You only have to do it like once you leave calculus, people don't tend to write limit like this, they tend not to do this. Since this is the class where you're learning this in, and this is the class where we're learning standard, you have to write limit. So you don't have to do it for the rest of your life, but for this class, you're going to have to do this. So we're going to go ahead and write limit as A approaches infinity. Okay? And then all I'm going to do is integrate this. We're just going to have x plus 1 raised to the negative 2 divided by negative 2 going from 3 off to A. See, I don't have infinity. Let's clean this up a little bit. So this is limit, A goes off to infinity. Get a negative 1/2 out front. This means I've got x plus 1 raised to the negative 2 going from 3 to A. Now, see this negative sign out front here? I'm going to go ahead and swap my limits of integration to get rid of that negative sign. So we're still going to have this limit, right, as A goes off to infinity. Okay, we have a 1/2 because 1/2 can go out through the limit. Okay, I've got x plus 1 raised to the negative 2 power from A to 3. That's where I swap my integration. That's where the sign went. So we're going to go ahead and say this is 1/2 limit as A goes off to infinity of 3 plus 1 to the negative 2 minus, brackets here, A plus 1 to the negative 2. Okay, that's what we have. So what we're going to have here, we have 1/2. Actually, we're going to evaluate the limit, so I don't think we write it just one last time. We're going to evaluate this limit. 3 plus 1 raised to the negative 2, that's going to be 4 raised to the negative 2, so that's going to be 1 over 16. Minus, and now we're going to let this A go off to infinity. If you really wanted to rewrite this for just a moment, it's going to look like A plus 1 squared. So A goes to infinity here. And as A goes off to infinity, you remember from calculus 1 that this whole thing goes to 0. So we actually just end up with 1/2 times 1 over 16. No more limit, we evaluated it. It's just going to be 1 over 2, and we're done. That's how you evaluate proper A. Let's do a few more. Let's do a couple. This one is a pretty famous type of problem. It's like one of the canonical things. Like once you get out of calculus, this is a thing you should realize. I want to go from 1 to infinity. So improper integral, because that's what it's actually 1 over x dx. So this is going to equal to the limit of b goes to infinity. Like I said, use whatever letter you want to use. Again, I would caution you not to use c's or e's, i's, but small i's, but things that don't already have a job. We're just going to go from 1 to b, 1 over x. Now you could just integrate this at this point, that's fine. Just going to type this as limit e goes off to infinity. And then we're going to have natural log of x going from 1 to b. So that's all we do here. So we're going to sort of say we have limit e goes off to infinity. I have the natural log of b minus the natural log of 1. Going back to algebra, right? Natural log of 1, what is that? That's 0. And then the natural log of b, like, is going off to infinity. Remember what the graph of natural log looks like? Looks something like this. So as b is going off to infinity, right, this is getting bigger and bigger and bigger. Slowly, but it's still getting bigger and bigger and bigger. Right? So the natural log of b goes off to infinity. So we would end up saying we have divergence. Now, math is kind of funny in the way of how we made things. That's just the way that if your function settles on a specific value, you can say that it converges, and it would actually converge to a point, to a value, like 1 over 32 in the example we did. If it doesn't settle on a value, it goes off to infinity, flip-flops between two values constantly. Then we say it doesn't converge, it diverges. So divergent doesn't mean that it always goes off to infinity, it just means that it doesn't settle on a specific value. We don't want to write down it goes off to infinity. We want to say diverges. So the integral diverges. We don't really say what diverges. You can say it diverges off to infinity. Mostly we're just going to say it diverges. Figure that people are going to figure out what we meant by that. So that's what we do for those things. Okay. There's a pretty famous example as we have 1 over x. If 1 over x goes to infinity, it should go to 0. Well, yeah, but the integral of it goes off to infinity, it diverges. So we have a bit of a problem with that. So this 1 over x idea, that's like a break. If the power is a little bit bigger than 1, then we're going to converge. If it's a little bit less than 1, then we're going to diverge. So if you have 1 over x2, then say the p from 1 off to infinity, x. If your p is greater than 1, by a little tiny bit, then we're going to have a convergent. That'll be fine. Okay, if I actually settle on a value, we'll be able to say something about it. Okay. If your p is less than 1, again, even by a little tiny bit, then the integral will diverge. So 1 is kind of a break point, but 1 diverges. Okay? And then you'll see a lot of integrals, you'll see a lot of problems, and I'll do one right now. Okay? So if I want to go 1 to infinity of 1 over x to the 1.0001. Okay, like. So we're going to go ahead and change our here. So let's say a goes off to infinity. We have the integral of 1 over. Actually, I'll rewrite it as a calculus problem. So we want to start taking one here. We have x to the negative 1.0001 x have 1. And the same rules apply there. We're just going to add 1 to the top and then divide by what we have left. So this is going to be the limit. A goes off to infinity. We have x to the, I add 1. We have negative 0.0001 divided by negative 0.0001. Okay? And we're going from 0 to a. So let's go ahead and type these things in. Actually, let's do one more thing first. Let's say that this is change our signs, change the limits of integration. This is the limit, so a goes off to infinity. Okay. X to the negative 0.0001. We're going to be going from a to 1 divided by 0.000. So leaving 0 in here. So now we're ready to go ahead and put some numbers in. So if I have 1 to the negative 0.0001 divided by 0.0001 minus a to the negative 0.0001, so 0.000 divided by 0.001. A is going off to infinity. This is really a fraction. So this whole thing is going to 0. And what we're going to end up is 1 raised to 1 raised to anything, right? As long as it's finite, 1 raised to a finite power is going to be 1. Okay, so remember there's a L'Hopital's rule problem. Don't have finite. We just get 1 over 0.0001, which I believe is 10,000. So that's what we're going to have for that value. It converged on a value. It was a big value, but it still converged. It settled on one specific value. Okay, let's do one in the other direction. Let's go ahead and take the integral of 1 over x to the 0.999. It's just a little bit tinier than 1. We're going to go from 1 to infinity. Yes. So let's go ahead and set this up. So we've got limit as a goes off to infinity from 1 to a of x to the negative 0.999. Yes. Same rules apply. We're just going to integrate this the same way we always have. So we're going to end up with limit a goes off to infinity. We're going to have x to the, we're adding 1, so positive 0.0001 divided by positive 0.0001. And we are going from what? From 1 to a. We don't have a negative sign in here, so we're just going to go ahead and set. So we've got the limit a goes off to infinity. A to the 0.0001 divided by 0.00 minus 1 to the 0.0001 divided by 0.000. Okay, even though this is going to go slowly, right? Eventually A will get really weak. This problem is going to take off to a positive. Slowly, but it'll still take off to a positive. So this is going to be infinity minus 1, minus 10,000. But infinity minus 10,000, we don't care about 10,000. It's just going to be infinite. This integral diverges. Okay? That's all we have to do with that. Okay, so once we know it diverges, we don't evaluate anymore. Right. So that is how you would do that. So generally, when you see like the integral with the value less than 1, you say, okay, I know that this thing is going to diverge. 1 over x, and it's just 1 over x, it's going to diverge. Take a little educated guess there. If it's bigger than 1, it's like, it's going to converge. Yeah, make it integrated, make it an educated guess. We still go through the integral, but it's nice to have an approximate idea. What should I expect here? Should I expect it's going to converge or diverge? So we go ahead and work the problem. And we do one that's a little bit harder for us. Okay. And we're going to go ahead and integrate from 0 off to infinity of x e to the negative x. So here we've got a couple of things going on. First off, we're going to change the limit. Okay, so a goes off to infinity from 0 to a of x e to the negative x. Now, I can't integrate this the way it sits, right? We have a polynomial times an exponential. Do you remember a couple of lectures ago when we said you have to do integration by parts for something like this? So we're going to say let u is equal to x, du is equal to dx. dv equals e to the negative x, d equals x in here. D equals negative e to the x. So we still have limit. So we haven't evaluated anything yet. So we have limit as a goes off to infinity. UV. So we have x e to the negative x minus a negative, minus this negative right here. So plus we have integral e to the negative x dx, right? It's uv minus v du. So I'm hoping that maybe if you didn't practice these enough yet, keep practicing them. They're really important. See these a lot. Technically, we all evaluate this from 1 off to 1 or 0. 0 off to a. Okay, we're almost done. So we're going to say limit a goes off to infinity. Actually, when I do these myself, I pretty much make sure everything hits on the left-hand side, so I can just recopy this limit as often as I need it, so I don't forget to put it in there. So we have x e to the negative x plus, we go ahead and integrate this. We just get negative e to the negative x, and we're going from 0 to a. Okay. So let's go ahead and fix this a little bit. So we're going to say this is x. I'm going to say this is x over e to the x plus, or actually rather minus. Okay. So that's e to the negative x is really a 1 over. So we've got minus 1 over e to the x. We're still going from 0 to a, but don't let me forget to write in this limit. So we have to go through and do this idea for x or a is going to infinity. Now, if you look at this first one, you might say, oh, wait a minute, we have infinity over infinity. That's L'Hopital's. So if we go ahead and try this, right, we're going to get infinite over infinite. This is an indeterminate form. Minus, if I plug in a here for infinity, we have 1 over e. That's just going to be 0. So that one's not going to be too bad. But you might have to figure out, like, oh, we have the limit as a goes off to infinity, right, of x over e to the x. We're going to go ahead and use L'Hopital's on this because we have an indeterminate form. Taking the derivative at the top, we just get 1. Taking the derivative at the bottom, we just get e to the x. We still have limit as a goes off to infinity. And as we break this in, I'm like, oh, this is just going to be 0. So this limit part is going to be 0. I did forget to put in, right? I got so excited about doing the limit, I completely forgot about what happens at 0. So we get 0 e to the 0 minus e to the 0. So we have 0 minus this stuff right here. Well, 0 times 1, 0. So we have 0 times 0 minus 0. Have minus 1 here. So we have negative 1, which will actually turn into a positive, and our positive 1 sitting. So the integral of e to the negative e times x times e to the negative x from 0 off to infinity, that turns out to be. That's a pretty popular integral that we'll see later on, and we'll get into some applications. You'll see this form a lot. Okay? So when you're doing your improper integrals, remember to write down your limits. Again, you're grading you on, this is part of your grade here. Okay, so remember you're writing that limit all the time. Always confusing, it's hard to get the proper notation on this thing, but that is one of the things that we will be asking you to do, is get this proper notation. After that, we just integrate as normal. And that seems like a reasonable endpoint for that lecture, so I will let you go practice. Thank you very much for watching, and I will see you in the next video.